First, I was going to play a video that was put together by Bernadette and the Brookhaven staff. They interviewed Dad, my father, James Powell, and it's a short six-minute video or so where Dad talks about the invention of Maglev. So I thought it would be a good way to start.
I first came to Brookhaven National Lab in 1956. I was fresh out of graduate school at MIT. It was a wonderful place. I'd been an intern at Brookhaven the year before when I was in my junior year. I spent some time up there and worked with people, and it convinced me that I wanted to come to Brookhaven. So when I finally finished my thesis in '56, I said, I applied, and I came to Brookhaven. It was just a great place to work. I really enjoyed it. What happened was I was in 1959, I was on my way to see a girlfriend up in Boston, Massachusetts, and I got stuck in a 5-hour traffic jam on the Throgs Neck Bridge. And I was just sitting there in the car, and I thought, there must be something better way to get to Boston. And I thought, well, there's trains and so forth. And then I thought, gee, what if you used superconducting magnets to levitate vehicles and have them travel along a track? And that's where it just initiated right there. And so I went back and talked to Gordon about it, and then we worked together and for several years. And then now, in 1966, we published our first main paper on it at the American Society of Mechanical Engineers conference in New York City in the fall. And it just caused a tremendous burst of interest. We had people coming from Japan, from Germany, other countries. I got a call from somebody in the U.S. Department of Transport saying they had 50 proposals coming in for magnetic levitation. So it just took off. What we really invented was not maglev per se, because maglev had been an idea that had been around for a good many years. There was a Frenchman called levitation who used alternating current loops to induce currents in a aluminum plate, when he was thinking that maybe we could levitate things like that. And even Robert Goddard, the father of rockets, got interested in maglev. He was proposing it and so forth. But they were all working with permanent magnets or electromagnets. And you don't get enough force, and it's hard to, with permanent magnets, it's hard to make them stable. So what we came up with was saying, well, what we want is a maglev system that has very strong magnetic lift powers, that's inherently stable, that you don't have to control it with a computer or anything like that, and that has a very large clearance. You don't want something that's a 1/4 of an inch clearance like you get with permanent magnets. You want something several inches, because for safety reasons, for debris on the track reasons, and so forth. And we realized that superconducting magnets gave you that capability. When we published the paper, we realized that we'd basically solved all the problems, and to confirm, we were confirmed in that belief in the 1966 paper, when right after that we had all these people visiting us. Every 3 or 4 months, we'd get a team from Japan saying, give us more detail, give us more detail. And we told them everything, We had automobiles, we had trains, we had ships, we had airplanes, and those are all kinds of modes of transport. And now maglev is another mode of transport that's just coming into play. At the maglev competition, this is a good example of encouraging kids to think for themselves and to build things that meet a particular goal. They have, I think, what is it, 5 tracks, kind of different activities to do with Maglev, like how fast can it go, what kind of hills it can climb, how is it propelled, what the best design is. So the kids from the various places, individually or in a small group, can enter their Maglev thing that they've constructed and test it with respect to these various activities. And then, of course, they're judged and see which ones are best and so forth. But nobody's telling them how to do it. They're doing it on their own, and that's very important. When I addressed kids after the contest, I tell them that this is the way. Think for yourselves, pose yourself a problem, decide what the best way to do it is, test it. And that's the way you should proceed in things. I do add one thing beyond just being curious scientifically or curious, wanting to build things or so forth. I say, don't neglect the humanities. I find the humanities are very important. I grew up that way, and reading books and reading poetry and listening to music, and I say you have to combine your scientific and technical curiosity with an idea of what the world is around you. Just pleased that they're enjoying it, and that they're learning something from it, and that this will persist with them as they get older and grow up.
So I thought that was a great way to start off this this talk. Dad and Gordon, and I'm going to refer to them as Dad and Gordon because saying Dr. James Powell and Dr. Gordon Danby is just weird to me. 50 years ago, they started off with a really revolutionary idea that the world is just catching up to today. And my hope is to explain the history over the last 50 years and then talk about where that idea is going to take us in the next 50 years, hopefully. And it's a real honor to be here at Brookhaven. I have such fond memories of going to Dad's office or lab, and Brookhaven at that time was filled with this excitement and this energy of innovation and creativity. And besides occasionally stealing those U.S. government pens, I just got a real charge out of being at Brookhaven, and it's probably what inspired me to become a scientist myself. So being back here at Brookhaven is fantastic. I think, let me get this correct. And Lee has already introduced the players in this play, but Gordon was born in Canada, did his BA in physics and math at Carleton and his PhD in nuclear physics at McGill, and came almost very soon after that to Brookhaven, to Long Island, and has worked on a variety of projects in the accelerator department, designing magnets for particle accelerators, and has had a huge impact in that field. The AGS, of course, was famous and contributed to Nobel Prizes, one here at Brookhaven, but he's also worked on the Muon G magnet and designs going into the Tevatron, and I'm not sure, perhaps even the LHC. His contributions to this field have been long-lasting, and many of you probably know Gordon in this room and know his contributions. Like many scientists and engineers from that era, he got to work on a variety of different projects. He's also well known for his work in MRI machines, as Lee was saying, and changing the MRI experience from the patient from being stuck in a coffin-like tiny tube up to an open, more patient-friendly experience and a better MRI machine is what Gordon is known for. And so every time you get an MRI for a sprained knee or whatever, Gordon has had a part in that. Dad was born in Pennsylvania, got his degree in chemical engineering from Carnegie Mellon, and then a PhD in nuclear engineering from MIT, or actually a science doctorate. And he was the first graduate from that program in nuclear engineering from MIT. Went on to develop the particle bed reactor, worked in nuclear thermal rockets. There were, of course, a lot of defense applications in nuclear thermal rockets, but I think the longest reaching impact of nuclear thermal rockets is eventually NASA seems to be working their way back towards using nuclear thermal rockets for exploring the solar system. And I read just the other day that Russia is actually considering sending nuclear thermal rockets to Mars. Who knows if they'll follow through on that, but there are better ways than the old rocket technology. And then one of his inventions was a way to vitrify nuclear waste in a modular fashion so that you pour your waste in to this graphite crucible, and you pour in some sand and you heat it up inductively to a few thousand degrees, and you immobilize that waste in glass, and then you take the crucible and put it off at some place like Yucca Mountain. We have an enormous amount of nuclear waste in this country, specifically places like Hanford with the tons of plutonium that are right next to the Columbia River. We have to start thinking forwardly about how to secure this nuclear waste. Now, also, like Gordon, he got to work on many things over his career. Fusion research, ball lightning, MHD. But what Gordon and Dad are best known for outside of the lab is Maglev. And they're lucky to have come to Brookhaven when they did. It was really a golden age for science and engineering. There was plentiful funding. There wasn't a lot of red tape. You didn't have to spend all your time in committee meetings. And if you were scientifically curious about something, you could follow up on that fairly easily. So the third player in this is actually Brookhaven. Brookhaven was a really magical place during the time when they came up with Maglev. And Gordon and Dad actually, when they got to Brookhaven, they were roommates for 3 years, from 1959 to 1962. And it was that community of innovation and cooperation that allowed them to collaborate and form this lifelong collaborative partnership. So before we go into the history, let's say where we are right now, today. Central Japan Railways has broken ground on their new Maglev route traveling from Tokyo to Nagoya. It's using the same superconducting Maglev design that Dad and Gordon proposed way back when in 1966. And it uses the key innovations from that. The Japanese have been working on Maglev for decades now, and they feel confident that they've got the system completely engineered for commercialization. This is going to be 286 kilometers long, and it will take you about 40 minutes to get from Tokyo to Nagoya. It's a testament to the commitment that the Japanese have had to Maglev this whole time. Because they're building it through the Japanese Alps. And when I say through the Japanese Alps, I mean literally through the Japanese Alps. About 90% of it is in tunnels. And these tunnels, in some cases, are 1,400 meters below the surface. It's a mammoth project. And they've committed to Maglev for this project. It should enter in commercial service around 2026. Namely because it's going to take 10 years to dig all those tunnels. Now, here's some news clips of that commercial vehicle at the Yamanashi test track. And they've been working on multiple vehicles since 1997 at this test track. This is the L0 vehicle. And it travels at, their top speed has been 600 kilometers per hour, or 370 miles an hour. And over the course of the last decade and a half, they've conducted hundreds of thousands of kilometers of testing in distance traveled, tens of thousands of passengers carried in these vehicles. And Japan has really taken the lead in global maglev development. So much so that Japan is hoping to bring this technology back to the United States. And they're hoping to build a Washington, D.C. to New York line that would take an hour to travel between those two locations. The Japanese have even offered to put up half of the construction costs of the first leg of that journey between D.C. and Baltimore. That would be a 15-minute ride between the two cities. And things are looking pretty good for that. They're moving forward pretty steadily. The DOT has funded the route studies and some of the environmental studies to the tune of $28 million, and Maryland has granted a railroad franchise to the company, and they're pretty optimistic about building maglev in the United States. Now, before I get into the history, I'll give the 2-minute primer on how maglev actually works, and we'll see how successful this is. Maglev, at its core, is a really simple idea. You have a vehicle, and the vehicle has magnet modules on the corners, the end corners of that vehicle. So it's basically just a box with magnets on the corners. Each of those magnet modules contains a loop of superconducting material that, so long as you keep it below its threshold temperature, it will continue to carry current in that loop indefinitely, generating a magnetic field. Now, the trick is keeping the temperature low enough. The Japanese maglev system uses low temperature superconductor, which means that the temperature has to be kept at liquid helium temperatures 4 degrees above absolute zero. And that's been a large part of the engineering challenge for maglev, is the use of low temperature superconductors. But obviously it works. They've been using it for decades. Now, when you have this magnet on the vehicle and you move this magnet through a guideway, the guideway has normal metal conducting loops. It has a set of loops for levitating the vehicle and a set of loops for stabilizing it laterally from side to side. And the magnet moving through this guideway with the metal loops induces current in these metal loops, such that those metal loops now generate their own magnetic field. So you have magnetic fields on the vehicle and magnetic fields in the loops interacting. And that's what generates the dynamic suspension. So this is the first key concept that Danby and Powell came up with, which is the superconducting dynamic stabilization. And another concept was that so long as the vehicle is in the equilibrium point at the center of where it's supposed to be, it won't induce any excess currents in those loops. So if it moves a little bit to the side, then all of a sudden there's a net current that's generated that pushes the vehicle back towards the center. And likewise, if it is depressed or elevated beyond its equilibrium point, the restoring forces of those induced currents will move it back towards the center. And that depends on the geometry of the loops that are in the guideway. This is called null flux loops. And then the final key concept that makes maglev work is how do you propel this vehicle? And so I've mentioned that there are levitation loops and stabilization loops, but there are also propulsion loops embedded in the walls of the guideway. And these are the only loops that are actively powered with AC power. And so the magnets on the vehicle have a north and south polarity, and charging these propulsion loops in the guideway creates a north and south polarity. And if you do the geometry just right, you can set up a situation where the vehicle is being pulled down the track and also being pushed down the track by the positions of these magnets. But what happens when the vehicle moves forward just a little bit? Well, because it's alternating current, then all of a sudden the polarity switches and it continues to be pulled down the track and pushed down the track as it goes along. And this is called the linear synchronous motor. And this was the third of the key innovations. So the Japanese system incorporates the electrodynamic suspension, the null flux loop stabilization, and the linear synchronous motor. So with that short explanation of Maglev and how it works, the idea has been around for a long time. Whenever you have kids with refrigerator magnets trying to push them together, the idea always comes up, how can I turn this into a vehicle? And going back to Émile Bachelet and Robert Goddard, the father of American rocketry, they both thought about maglev and how to use maglev for transportation. The problem was electromagnets and permanent magnets don't have the lifting force. Goddard particularly was very forward-thinking. He had a patent in 1950 that put his maglev vehicle in a tube without air, an evacuated tube, so that he imagined maglev systems going thousands of miles per hour. But without the superconductors, the system is not practical. So as mentioned, Dad's eureka moment was on a bridge, stuck in traffic, and he realized that superconductors were the way to go. And they were a hot topic in research back then also. But these ideas take a while to evolve, to iterate. And so Dad, in addition to his day job, was able to think about it for a while. And in 1963, actually that would be the first superconducting maglev paper, but it was a preliminary or primordial maglev, if you will. The first idea was, let's put superconductors in the track. And he built little models. This is kind of hard to see from the scans. It was a 2-foot diameter test track and levitated a vehicle that went around it. This is it levitating. And the idea was to use superconductors as the rails of the track. But if you, that doesn't work out at the larger scale because you have thousands of miles of network of transport, and to build superconducting tracks everywhere would not be economical. So that's when Dad started working closely with Gordon on how to make this a practical system. And in 1966, at a conference in New York, they presented high-speed transport by magnetically suspended trains. And this really laid out some of the key concepts that became modern maglev. Put the superconductor in the vehicle, not in the track. Use the electrodynamic suspension. And this was the first presentation of the null flux loop design. And as mentioned, this generated an enormous amount of interest at that time. The United States at that time had a program called high-speed ground transportation, and they were funding research into this. And so this idea really took off. They applied for their patent in '67. I don't think it was granted till '69. And then in '71, they presented the last piece of the maglev puzzle, which is the linear synchronous motor. And that was also at a conference, this time in Boston. Now, this was the first formal description of a linear synchronous motor. And it was revolutionary because the motion is controlled by the track, not by the vehicle. The frequency of the AC power is what determines your speed and acceleration. And something that's not really appreciated is that what this means is you can never have a maglev vehicle overtake another maglev vehicle because they're locked into the same AC frequency. You can never have a maglev vehicle collide head-on with another maglev vehicle. So this is envisioning a method of transportation that is inherently safer than rail. Both Germany and Japan jumped into maglev with both feet. Germany initially was looking at superconducting maglev, but they decided very early on that they would go with electromagnets, electromagnet suspension. And the reason for that was that superconductors were still a very new technology, and they thought they could get to market quicker with traditional technology. So they built test tracks, and they iterated on their design and came up with the Transrapid system. And some of you may have ridden on the world's first high-speed commercial maglev system, which is the Shanghai line between the airport and the city. But ultimately, the drawbacks of the German approach caught up with them in that you have a levitation gap of maybe a 1/4 inch, as opposed to with superconducting maglev where you have a levitation gap of 4 to 6 inches. And also you can't lift large amounts of cargo with such a system. So you're destined to only transport passengers with this system. Because the levitation gap is so small, that means your track has to be engineered to a much higher precision because you're going several hundred miles an hour, which makes the whole system much more expensive. Eventually, the German government decided to decommission the test track. This was after an accident, which wasn't related to the maglev part of it, but somebody left a maintenance truck on the track, and then the vehicle collided with it. There's still some effort to try to get Transrapid deployed in locations around the world, but it's not going to happen in Germany, and it probably won't happen elsewhere either. In contrast, Japan has always been very much behind superconductors and superconducting maglev. They took the ideas of Powell and Danby and really ran with them. Over the course of many decades, they had multiple test tracks and many different iterations of their vehicles. In '97, they opened their last test track, Yamanashi. Dad and Gordon were invited to give the commencement address there, and they were honored as the innovators of maglev. And now, as I mentioned, they are ready to commercially deploy superconducting maglev. And it's been a 50-year process, and that just highlights how far ahead of their time Dad and Gordon were with superconducting maglev. Now, if we turn to the US, it's a different story. There's been a lot of stopping and starting in the US. There was a burst of activity right after the publication of the paper. Teams formed at MIT and Stanford and Ford. And this was all under the aegis of the high-speed ground transportation program. But the funding never materialized, and these programs petered out in the mid-'70s. And maglev development lay moribund for over a decade until Senator Patrick Moynihan came along and realized how much potential this had for this country. He formed a technical advisory committee. Dad and Gordon were the co-chairs of that committee. And he spearheaded a new National Maglev Initiative program. And this program would have funded maglev technology development in this country to the tune of $1 billion. And it was visionary and far-reaching, and ultimately killed, because laws can be passed in this country, but that doesn't mean we're going to allocate the money. So the money was never allocated, even though the initiative passed. Moynihan was persistent, and a little bit later on in the late 90s, he spearheaded the National Maglev Deployment Program. And the reasoning there was, well, okay, you won't give us the money to develop new technology in maglev. Let's build a demonstration track somewhere in the United States. And when Americans see maglev in a city, they'll want to fund this at a national level. So the National Maglev Deployment Program was offering money to build one demonstration track. There were 7 teams competing for that money. 6 of them used German transrapid technology, and one American team used superconducting maglev technology. And that was Maglev 2000 of Florida, which Gordon and Dad were the founders of. Now, there was no real money in this program for technology development. So like the true Brookhaven scientists they were, they found money wherever they could. And with basically $5 million, they reinvented maglev and generated a whole new generation of maglev technology. But unfortunately, that program was also killed off, and the money was never released to build a test track. So it looks like in America, what will wind up happening, unless something changes, is that we might wind up buying our maglev technology from Japan, which is an excellent system, but it's telling that we invented this technology here, and other countries had the foresight to really develop it. This is just a rough approximation of the scale of funding. We've dedicated a few tens of millions of dollars to maglev, and almost all of that was paper studies and root studies and not actual technology development. Germany and Japan have dedicated billions of dollars to this. And so I think that speaks for itself. One bright spot did come out of the National Maglev Deployment Program, and that was the Maglev 2000 of Florida Corporation. This is the Japanese design. It's got the characteristic U-shaped guideway with magnets on both sides interacting with that guideway. The Maglev 2000 second generation design is able to use monorail configuration or flat planar configuration that is flanking existing railroads. And this same vehicle can travel on both. There's no need to change the vehicle design at all. And so I'm going to get into some of the advantages of this second design in a second, but one of the major reasons maglev hasn't taken off in this country is because we are unwilling as a country to fund passenger rail. And so one of the great insights that Gordon and Dad had was, well, we're going to have to change maglev so that it can fund itself. There's no passenger rail system, high-speed passenger rail system in the world, I think, that is self-sustaining in terms of funding. Everything requires government subsidies, large capital expenses, and the US is just not willing to do that, apparently. So one of their key insights was, well, we can adapt maglev to make it ultimately profitable. So the second generation design is centered around the quadrupole magnet. So easy way to describe the quadrupole is the Japanese has a dipole magnet, which is a simple loop of superconductors. Now, if you take a second loop of superconductors side by side with it and you run the current in the opposite direction, you have a quadrupole magnet, so that you have 2 loops of superconductors here. And this is just a CAD of the prototype they built. If you look at the cross-section of that, then you have these orange dots, which are supposed to represent the superconductors. And one of the advantages of this design is that you have a symmetric field on both sides and on the top and the bottom. And that allows you to run both on vertical panels situated on narrow beam guideways and horizontal panels flanking railroads. Another advantage of the quadrupole design is that there's much lower fringing magnetic fields. The field strength drops off much faster than the dipole design. So you notice in the Japanese vehicle, they put the magnets way out at the ends of the vehicle. And that's because they don't want the passengers to experience elevated magnetic fields, especially if you have a pacemaker or something like that. But with the quadrupole, because of the lower fields and how they drop off with distance, you can place magnets along the entire length. And that means that you can lift much heavier loads with your vehicles, which means now you can carry freight in addition to passengers. So the four main advantages that their system provided is because you have this planar mode of travel, you can interloop planar guideways so that you can have a electronic switch, although the second half of this GIF is supposed to show a vehicle going off on the other route. There are no moving parts with an electronic switch. If you imagine the Japanese system in the U-shaped guideway, how are you going to get from one route to the other? You have to move the entire 1,000-ton structure from one route to the other, and it's a very slow process. Another advantage is with narrow beam guideways, which you're going to be running between cities, and most of the network is probably going to be narrow beam, everything can be pre-manufactured very inexpensively in factories so that you build these components, the beams, the pillars, the footings, you ship them to the site and they are snapped into place instead of custom construction, as is the usual with large-scale infrastructure projects. Also, because it has this planar guideway mode configuration, you can use existing railway infrastructure. So when you're traveling between cities on a narrow beam, that's great, but how do you get into the cities? Well, because you can go on existing railroads, you just switch to commuter line railroad or eventually transit, and you can go right into the heart of the city and use existing stations. But the most important advantage of this new approach is because you can carry freight, you can capture some of the $500 billion we spend every year on intercity trucking. And this is what makes Maglev affordable in this country. Capturing 10 or 20% of the freight market would pay for the guideway and pay for all the operations and maintenance. So with their $5 million budget, shoestring, Maglev 2000 designed the quadrupole magnet. They built quadrupole magnet prototypes. They tested these prototypes. And these were full-scale prototypes, as would go on the vehicle. They built guideway loops, panel sections. They built a chassis for a vehicle, an aero shell for a vehicle. They built guideway beams. All this for $5 million. And unfortunately, the government did not fund the development to the point where we could have a working test system. So we've tested components, but everything is there ready to take to the next level. So again, this is a 50-year-old idea. Why haven't we moved forward on this? And obviously one aspect is politics. There's a lot of vested interests with the airlines and with the auto industry. But a large part of it is misunderstandings or misconceptions about Maglev. And then we need to think bigger about what we can do with Maglev. A major misconception is that Maglev is some sort of high-tech technology, like flying cars that's always out there in the future. And in reality, Maglev is much simpler than all the other modes of transportation. All you have is a loop of superconductor that if you keep it cold, it just works. There's no moving parts, there's no wear and tear, there's no complicated control electronics in the vehicle. The vehicle is basically a box with magnets on the corner. It's an elegant system with an elegant and smart way of connecting the parts. Compare that to jet engines, which have exotic materials in the turbine blades, or internal combustion engines with thousands of parts, and all the electronic control systems that are now in these parts. Maglev is much simpler and ultimately will be much cheaper than all the other modes of transportation. Another misconception is superconductors are made of magic pixie dust, and how can we have a transportation system based on superconductors? Well, superconductors obviously have been working commercially for decades now with MRIs, and particle accelerators use thousands and thousands of superconductors, magnets that have to work 24 hours a day, 7 days a week, year in, year out, without fail. It's a well-known problem. Most superconductors today are still low-temperature superconductor magnets, but the cost of high-temperature superconductors is coming way down. In the last decade, or a decade and a half, they've come down between 5 and 10-fold. The cost of low-temperature superconductors for about a meter is about $1 per meter. Today, you can get high-temperature superconductors for about $100 a meter, or maybe $50 a meter at volume. But we think that the cost is going to come down by another order of magnitude. Already today, the cost of building a maglev vehicle is cheaper than what we would pay for the Long Island Railroad two-car unit that they use. And when it comes down by another order of magnitude, remember, it's just a box with magnets on it. There's no real expense in building these vehicles. Another misconception is that maglev is a really, really fast train, and we already have trains, why do we need them? Problem with trains, with high-speed rail, is that it's expensive to build and maintain. The tolerances for making a 200-mile-per-hour rail, with all the stress that you have on the steel wheel rail, it's an expensive proposition, especially because you can't carry freight. So the passengers then have to subsidize that. And traveling to Washington, D.C. on high-speed rail is expensive. It's $170 or something like that. It shouldn't be that expensive. Maglev, every vehicle is its own locomotive, in effect. So that means you can dispatch single vehicles wherever you want. And remember, the vehicles don't control their location. The network controls their location. So you can have dynamic, algorithmic scheduling to meet demand. If a ball game gets out, the network sends a bunch of vehicles to that location. It's freight capable, so it will pay for itself. And ultimately, this means that passenger fares will be very low. It will be a profitable system. And this is why I think in the next 50 years, you're really going to see a renaissance of maglev in America. We have a problem. Everybody knows about our crumbling infrastructure. Society of Mechanical Engineers gave us the national infrastructure a D-, 3.6 trillion needed just to maintain our level of service by 2020. But we're going to double passengers and freight by 2040. Congestion, delays, and accidents cost hundreds of billions annually. And if we're going to be spending all of these trillions of dollars, not sure if that's me beeping, then why continue to prop up an older infrastructure system? For less than $1 trillion, it's possible for this country to build a 29,000-mile maglev network where 74% of Americans are within 15 miles of a station. This would radically decrease our greenhouse gas emissions and our dependence upon foreign oil. Building out this network would lead to millions of jobs, or at least hundreds of thousands of jobs, and it would be ultimately self-funding if you capture some of that interstate trucking freight market. And we should do this because our history, our economic history, has ultimately depended upon our transportation. If you look back over the last 150, 200 years, we've had one mode of transportation rise up after another, and they've all contributed to our wealth as a nation. Everybody knows about the transcontinental railroad and the interstate highway system and our aviation system. But the rate of growth of those systems has dropped dramatically, and we have nothing new coming in on the horizon. And Maglev, I think, will be that, something new. And although some people shudder to think about this, and I think Dad is included, in 20 years, nobody's going to be driving their own car. We're going to have driverless cars. It's kind of madness to think, and I'm biased here because I hate driving, and I'd rather bike everywhere if I could. It's madness to think that you're going to own a car that's going to sit in your driveway or in a parking lot 95% of every day, and you're going to spend all the money on that car and the expense needed to upkeep it. We're shifting to an Uber type of economy. And transportation needs and transportation assets are all going to feed into what's going to be the transportation cloud. So that ultimately you will be able to provision on demand exactly the assets that are needed. It's a much more efficient way of spending scarce resources. So one quick example, if somebody in Greenport, Long Island wants to go to a concert in Freeport, Long Island, if they tried to do that today by public transportation, they might starve or get lost along the way. It literally would take you about 6 to 8 hours just to get there. But in the future, you're going to hit a button on your phone. A car is going to show up at your door and take you to the Maglev station, driverless car. The Maglev vehicle is going to take you in about half an hour or 20 minutes down to the other end of Long Island. And then another car will be there waiting for you to take you to your event. What this basically does is it gives the convenience of a subway across a huge geographic area. And if you live in Manhattan, you never spend your day planning out timetables. You don't worry about transportation. It just works. This is what we need to start thinking about at a broad geographic scale. And I don't think I'll go into this because time is running out, but there are so many other applications of Maglev. You can use it to store large amounts of energy for wind and solar power by moving concrete blocks up and down hill. You can use it to move water across long distances and recapture some of the energy of that transport by going up and down grades. We did a study actually looking at how much it would cost to transport 1% of the Mississippi River from the Mississippi River to the West Coast, providing drinking water for 100 million people. And it was about on the order of $60 to $80 billion, which sounds like a lot, but for those 100 million people, that's a pretty good deal. And then you can, as Robert Goddard was saying, if you put Maglev in tubes and take all the air out, you can accelerate your vehicles at very high speeds, up to orbital speeds. Ultimately, I think this is the way that we're going to launch material into orbit for about 1/100th the cost of rockets. So there's a bright future for Maglev. And I think what was started 50 years ago is just starting to come out into the public view now. And I think let's see where we are 50 years from now. So finally, this is Gordon and Dad at the Franklin Institute winning the Franklin Medal in Engineering in the year 2000. And this has been a great ride, and thank you.